turn on in 13 seconds. I put a couple of references in that test, in this lecture that I started already last week, since I saw you last. The idea was that you can look them up. Unfortunately for this subject, it's such an old kind of subject that they don't have good literature reviews you can download like the ones for astrochemistry. There is one pretty good chapter I found from Phil Bunker, an expert on this, which you can find on the web today. Otherwise, any textbook in the library tells you about rotational spectroscopy. This one, I think, is particularly good, which you might have in the library just in the future if you want to get into the subject for some reason. That's a good place to start, actually. Added that. Okay. And so to kind of recap what we're doing a little bit, this shows most of the things we discussed. The idea is that if you're talking about spectroscopy of rotational levels or any other kind of levels, electrons or vibrations, I mean, the first thing you always want to do is calculate the energies of your levels. In this case, we have energy going upwards and the rotational levels, which are indexed by J. And so as you saw in the test, those have a formula. Which we'll ignore the D. That's a correction, which I won't worry about at the moment. And so once you know your levels, then you want to know your populations. And so your populations, that depends on the temperature, because these particles, these levels are all where they are because of the thermodynamic interaction between the particles. If you remember, this was the case of particles moving in a box. We have the distribution of their velocities. And this time I will write the formula up, actually. I decided. Now you can probably see why I didn't want to get into this really. But the important part of this formula is you have a lot of constants. This is the velocity. This is the probability. So it's a probability distribution. In fact, that's how you draw these curves exactly. And there's some constants here, which we won't worry too much about. The important part is here. We have an exponential, and this is minus half mv squared. That's the energy minus the energy of the kinetic energy of these particles. So basically, it's the kinetic energy divided by a kinetic temperature and Boltzmann's constant. And the point of all the temperature tells you really what, if you have a temperature of any kind of system, velocity or rotations, is what is the average energy of the system. So this is really the energy at some point on our distribution divided by the average energy. So that's kind of interesting. And the other kind of distribution was not thinking about velocities, but talking about rotational levels of the molecule. The fact that some are rotating faster and slower, meaning you can have a similar distribution at a rotational level about what the probability of a molecule having a particular kind of level of rotation is. And the formula for that one, which I did write up because you need it in the exercise, so in this case, you have some more constants. This is the degeneracy, which we talked about a bit, and the partition function, which we didn't talk about much, but is just a constant, and the same exponential dependence. In this case, you have the rotational energy and the rotational excitation temperature. So there's something a little bit universal going on here. And the reason it's an exponential is we can discuss in terms of the statistics of the of having a system of any kind of energy levels, whether it's velocity or rotation, and you can divide those into subsystems, and you can actually find a symmetry which makes it exponential. But that's not particularly important for the assignment later on. But there is a common theme here of these distributions. Okay. And then so the whole point here was to use this formula to tell us the population of these levels at a particular excitation temperature. So the first step of spectroscopy is to work out these levels. The second step is to work out these populations. And the third step is to work out the spectrum that you then see in space. And the spectrum is to do with, in this case, a photon being absorbed, making the energy level increase, or a photon being emitted, making it come down. So we need to know the difference in energy levels. And the reason we have a simple case here is if you want to know the difference between two energy levels, J equals 0 and 1, it turns out it happens to be 2b if you do the algebra on the energy levels. If we add the d constant, it messes up that nice pattern. So I left it out. So you end up with a spectrum where you know all the energy changes between levels, giving you the energy down here. And the energy of this spectrum can either be written as an energy in wave numbers. These are written normally in wave numbers. Or it could be a frequency in gigahertz. It could be a wavelength in nanometers. But these are all completely equivalent quantities like we saw in the first lecture. And so, yeah, so once you're at that point, you're then capable of either computing or simulating or measuring a spectrum where each point on the spectrum is related to the energy levels. The shape of the spectrum is related to the population that contributes to each possible transition.
Sorry, I'm a little lost. When you say population, what do you mean?
So, in this particular box, there's a box with particles in it. There's 9 particles. One of them is in the J equals 0 level. 3 are in the J equals 2. And so if we had a box that was the same box but had a higher temperature, more kinetic energy, more excitation energy, there'd be more particles higher up. So what that means is that at higher temperature, you see a spectrum which begins here. The J equals 1 to 0 transition is the lowest energy. That's this point. Higher and higher rotational levels all have a emission spectrum, emission line at higher and higher energies, kind of following this formula of energy levels, rotational constant, if you ignore D, which we will for now. And so that gives this shape of the spectrum. But the strength of each line depends how many molecules there are available at that energy to form this line. Yeah. So this formula is everything you need to know to say about where in the spectrum the lines will appear. And this formula is everything you need to know to say how strong each line will be. Or nearly everything you need to know, because that's what we're going to get onto next.
Okay, that moves that. Okay.
Because, yeah. Okay. So, just to remind you of this as well. The idea was that if you have a lower energy level with a population of 1, an upper level energy with a population of 0, and a photon is absorbed, then you have a population of the lower level of 0. Once that moves up, and the population of the upper level is 1. So we can write that either as discrete numbers, or we can write it as a differential equation, or as a derivative, because if we have 1 billion particles in a box rather than 1, we can still have a distribution, but with many particles in the first, the lower and upper level. So it's a kind of continuous problem. Anyway, the point is that if you have a particle in this level, N1, you have some radiation, and radiation in this case are represented by the letter rho, meaning there's some radiation around. And then per molecule, you have a particular constant which tells you the probability in 1 second of this radiation being around, it'll move up. And that means you can then describe the amount of particles in the top level increasing, depending on all those levels, whether there's any in the ground state at all, whether there's radiation, this parameter which depends by molecule. And at the same time, the distribution in the lower levels will decrease. That's why it's a minus sign. So there's a conservation of particles going on there as well. And so this is the case of photoabsorption. The photon is absorbed by the molecule. The same thing happens if the molecule emits a photon, just spontaneously, in which case the molecule goes down and you have a decrease in population in the upper level, and an increase in the lower level, which I didn't write. And the third case, which we won't get into at all, is stimulated emission, where you are in a photon field. Rho is the number, it means there's photons around. N2 means you have some population in the above, and that photon stimulates, it's not absorbed, but it stimulates the second photon being appearing. This is like what happens. This is the principle of a laser, or in fact, a maser, which you do see in space. Yo.
Does spontaneous emission has to do with radioactivity, and is that a way to recognize radioactive elements in space?
I mean, it is in a big enough viewpoint the same thing as radioactivity, but in this case, it's not radioactivity. I mean, in this case, if you have a in this case, the molecule has some energy stored within it. If it's in the lowest possible level, it's in its ground state. And I don't admit to know a lot about quantum field theory or anything like that, but the point is that if you have stored energy, then there's a probability just of spontaneously releasing it as a photon, which is exactly what radioactivity it is, but the stored energy in that case is inside, not the electrons around the molecule, in this case not the rotational state of the molecule, but inside the nuclei themselves. So it is the same thing, but not exactly the same. So this idea of a differential equation, meaning you have a decrease in population because a photon's been emitted, and it must have fallen in energy, decreasing the number of particles in the top level. Okay. So there was 3 constants there, actually. The first one we saw was this one. This is the absorption coefficient, per molecule parameter that controls how easily it'll absorb a photon. This was the spontaneous emission coefficient, which is the per molecule, no, sorry, this is the, this is the spontaneous emission coefficient, the per molecule coefficient describing how easily it'll create a new photon if there's already photons around. And the third one, which is the absorption coefficient from the ground state. And it turns out they're all actually related by these 2 formulas, which I won't get into, but we don't have to worry about those processes being independent. And they're all related by a more fundamental parameter. So we're talking about molecules interacting with radiation either by absorbing it or by releasing of the photon. And it turns out the fundamental property, it's not those. This one. Say you have a molecule, and they're small, so I'll draw it tiny. That makes sense. And this molecule is in a radiation field, meaning the parameter rho, which I showed earlier, is non-zero, but there's radiation around. And if you draw the radiation as an electromagnetic wave, what that means is that at this point, there's an electric field produced by this electromagnetic wave of the radiation that's around the molecule. But the critical thing is, because it's so small, it's only experiencing the electromagnetic wave in a small part of its period, a small part of that. So if you consider that point by itself, just make the molecule a bit bigger, like that. And what that means is that the shape of the electric field at this top part of the wave is virtually flat. It's only a small part of the electromagnetic, small part of the sine curve, so there's almost no curvature there at all. It's a flat electric field. Be the same as if you had some positive charges down here in a static problem, or some negative charges up here. And then the picture I've drawn here is found on the internet here, is an atom, molecule. This is a molecule like carbon monoxide or HD, hydrogen and deuterium, because you've got 2 different nuclei in the middle. And for that reason, you also have the electrons, that's the cloud of electrons, which is more attracted to one nuclei or the other, depending on which is the more positive charge. So you end up with a cloud of electrons, in that case, which is bigger on one side, smaller on the other. And so you actually end up with more electrons on this side, meaning the whole end of this molecule is negative and that side is positive. This is actually the polar or non-polar kind of molecules that there are. If you have this kind of electron distribution, which is uneven, you have a polarized molecule with a negative charge on one side and a positive charge on the other because of the adding together of all the electrons. And if you have an electric field and a negative charge, then you're going to feel a force downwards against the electric field. If you have a positive charge, you feel a force upwards against the electric field. And this is the principle of how radiation makes a molecule rotate. This is why it absorbs a photon. I mean, why it absorbs the photon with only the same energy as an energy level in terms of the rotational number J is more detailed, but this is the basic idea of how an electromagnetic wave, which is basically flat on the scale of a molecule, produces a torque, makes it rotate. And so that's what this picture was meant to be talking about. And so the amount of torque that each molecule produces is exactly this parameter mu, the transition moment u. Yeah, other parameters in here which we also need is J, so it depends on the rotational speed of the molecule when it's in this electromagnetic field. That's one thing. And nu. And so nu is the frequency. That's the normal. The transition frequency. And that is just related to the energy of the transition. So here we have the energy levels. You take the difference between levels, that gives you the energy of the transition. You multiply that by Planck's constant, you get the frequency of the transition. And this actually was the origin of Planck's constant, I believe, this exact relation between energy of a photon in a molecular transition and the frequency. Okay. And the really important point here is that this is not just nu, this is nu cubed. So if you have a transition which has a small frequency, like this one, this is the frequency of this transition, 0 to here, then it has a certain susceptibility to being rotated in an electric field. This means the emission constant will be bigger by a factor of cubed of nu. So this transition has an emission constant which is proportional to nu cubed. This transition also, because it's twice as large a transition energy, it's 8 times more likely to be, so it has an 8 times larger emission constant, meaning that a molecule in that level, even though it's the only difference is that it has a greater transition, greater amount of energy to lose if it falls down, is 8 times more likely to do it, which means it'll happen in 1/8 the time.
Where does that come from? Like, why is it not squares?
Yeah, that's a good question. I'm not completely sure, but I don't think it's a property of the molecular levels themselves. I think it's a property of the fact that when you have the photon, I mean, when this happens, so this is the emission constant when it loses energy, meaning it transitions from a level with J plus 1, say J equals, level 1 is 5, to a level J, so it goes from the J equals 5 to J equals 4 level. So the molecule changes, but the photon also appears. And I think this is more to do with the fact that the degeneracy of the photons that you're producing is also, I mean, if there's 2 ways to produce a photon, you have twice as more probability of it happening than if you have only 1 way to produce a photon. And the ways to produce a photon out of a molecule in the field is proportional to nu cubed. I think, if you find out a different fact, I think that's what it is. But the main point in this case is that I mean, a cube is a big dependence. If it's a squared, that's already something, but a cube is really something. Okay. All right, and so here I've written down some of these numbers. They're usually written in the units of dBi. So I've written this formula with a constant, so you can work out the emission the Einstein emission constant from the transition moment conveniently. And so this value mu, now this really comes out of the details of this electric field. So that's the quantum mechanics of many electrons. And it's kind of a parameter you either measure, most likely, or you can calculate with a supercomputer. Turns out it's very small with CO, quite large with CS, and somewhat larger again with a molecule HCN, 3 atoms. A 3-atom molecule also has the same electric field. But for H2, it's exactly 0. And the reason for that is, I guess, do you need both these projectors? I mean, yeah. All right, never mind. If you have the case of hydrogen, yeah, I mean, if I just have this one, can you see from there? Is that, yeah? Okay. That'll be good. Should we just turn this off somehow? Yeah. Yeah, if you can reach it. You're a tall guy. Okay. So imagine the same picture again, over here this time. And here I deliberately chose a molecule, maybe carbon monoxide, where you have more electrons on one side than the other. In the case of hydrogen, you have exactly the same charge of each nuclei, +1. And so you have a perfectly symmetric, well, I can't draw a perfectly symmetric charge distribution, but it is, meaning that here you have no charge, and here you have no charge on average. So if there's a torque, there's no torque. There's no asymmetry for a torque to act on. And it turns out the most important thing about whether or not this is 0 or not is how symmetric your molecule is. It's not just hydrogen. I mean, the same thing happens for oxygen, O2, or nitrogen, N2, and it happens for carbon dioxide as well. So it's no torque. Because carbon dioxide has the structure of a carbon atom and 2 oxygen atoms, but they're in a perfectly straight line. So the distribution of charges is not quite so simple anymore, but it is even about this line, so you have a symmetry. Whereas water looks pretty similar to hydrogens and so forth, but water has a structure like this. So you also have a very complicated charge distribution. And admittedly, if you draw a line here, you can have a kind of symmetry. This is like a mirror image. But there's no way to draw a line in this direction that produces a symmetry. So water does have a dipole moment. It does have a mu, which is more than 0.
So you could say that in every molecule that there's 2 atoms of the same element, there is no torque.
Exactly. I might even have written the statement up to that point. Yeah, okay. I didn't use the phrase, but the exact phrase you're thinking of is homonuclear. H2, O2, C2 also exists, N2. Means CO2 is not homonuclear because it's got 2 kinds of nuclei in it, but although that's also symmetric. Whereas heteronuclear is the reverse case. CH, CO. Like that. So that's exactly right. But you can have a more complex problem as well. In fact, I don't have a picture of it, but one of the most interesting molecules which you find in space is the C60. That's the formula. I won't draw it, but the formula is C60. So it's 60 carbon atoms arranged in a sphere, perfect sphere. And so that's a lot of atoms, but everywhere you draw a line, you find a symmetry. So it turns out C60 has no transition dipole moment either, because even though it's 60 atoms, because it's so symmetric. Yes. Okay, so so far we've talked purely about radiation. If you have an upper state and a lower state, radiation, in this case a photon gets emitted, it falls down out of the upper state. But this is not the only way that you can have a change of rotational state of a molecule. The other option is collisions, which I've drawn here. This is another molecule. The one we're talking about, if it's in its lower rotational state, if it collides with another molecule, that can induce a rotation. In fact, this is, I said at one point that if you have the kinetic temperature, that's the temperature associated with the velocity of all the particles in the box, and you also have an excitation temperature, associated with all the particles rotating in the box. But once they start colliding, then you can turn the kinetic energy into rotational energy and the other way around. So those collisions turn out to be as important as the effects you have from radiation. So we need to consider them both at all times, actually. Okay, so what this means is we have a surrounding gas. I've drawn a picture of an H2. This is meant to be an H2 molecule because in space, the most common gas is H2, where you have molecules. So in fact, it's more than just most common. 99% of the gas you find in the space where you find other molecules is either H2 or H, a hydrogen atom. But the point is this is almost always H2 that's colliding in space. On the atmosphere, the most common molecule is N2. So the most important collisional partner for this kind of thing is N2, but in space it's H2. Okay. So then we have a differential equation. And I've changed from J's to N's, but that's not too important. Okay, let's write it over Paul. Okay, so if a collision happens, then we have a change in population. This population is going down. N1 is going to N2. N1 is decreasing. It's negative. Whereas this one is increasing. And the amount they're increasing or decreasing by must be the same because there's no particles being created or destroyed, so that's even. So we can actually write one of these equations is enough. And if there was not one, but a number of particles in here, like a large number, then the chances of this, so in our box we have 5 particles, they're all in the lower state. The chances of a hydrogen molecule colliding with one of them and decreasing the number of particles in the lower state, increasing the upper state, proportional to this population. The more there are, the more likely something's going to happen. The other thing it's proportional to is how much of this H2 there is. So in this case, we're talking about carbon monoxide, another common astronomical molecule. And carbon monoxide is basically in its box, but surrounded by an ocean of H2. So we have to consider how many carbon monoxides are available to be excited and how much H2 there is available to do the excitation. And finally, there's a third parameter, Q. And so now we have the parameter which is not so simple. This is the parameter which describes all the collisional physics between an H2 molecule and something else. So Q is, if you like, it's like the Einstein A coefficient or the transition moment. It's just a parameter which, for our purposes, I mean, it's a very interesting field of research if you're into this kind of stuff to just calculate Qs. I mean, you learn a lot of quantum mechanics and things like that. But if you want to just keep work with the astronomical observations, this is something you look up in a table, probably. Okay, in this case, you actually have the same formula because they're just changing between the two levels. Okay, so that's basically just looking at this arrow. Another other thing can happen, we already discussed, is that an excited state can decay by photons. And that has a formula, the differential equation we already wrote out. So now a particle in a box not only has levels in the ground state, some of the particles are already in the excited state, meaning some of these particles can decay downwards and join the lower energy levels. So the probability that happens, the speed at which that happens depends on how many there are in the first place, multiplied by, multiplied by the Einstein A coefficient, the other, effectively, physical parameter we need to describe that part of the process. And that's exactly it. Those are the, if you consider two effects, collisions increasing the energy of rotation and emission decreasing the energy of rotation. And it turns out the interesting thing about this is that NH2 in space is on the order of 100 H2s per cubic centimeter. Doesn't, you know, it's in a small area, but it's a very small number of molecules. In the atmosphere, it's more like 10 to the 20 molecules per cubic centimeter. So in space, this number becomes very small. And what it means is that we no longer can assume that, that we have a thermodynamic equilibrium where these collisions and these photons are all piling on all the time, meaning that there's constantly changes of kinetic energy from the H2 with the rotational energy of the molecule we're interested in. That actually can be quite a rare event. If this density of H2 is small enough, then a collision can happen once per day or once per month. And what that means is that in that month, the chances of a spontaneous emission of a photon is almost certain. A photon can be emitted, for some molecules it can be emitted in a second. Other molecules it might take a few days or a few hours. But if this is a month and this is a few days, then pretty soon all the particles are going to be falling to the bottom level, and there's no collisions to push them back up again. So,
that has something to do with the thermal depth of the universe, or not?
probably. I think that might be more to do with the nuclear effects you're talking about before. I mean, I think the thermal depth of the universe, if you have all the matter not just be in a low rotational state, but if all the matter decays into not just matter, but decays into pure energy eventually, or all the hydrogen decays into very heavy atoms, then you have a thermal death. But the rotational states might not be important in that case. I'm erasing this equation because these two equations are equivalent. The levels must be on one side or the other. Okay. Okay. And so eventually, though, the number of particles in the upper and lower states will be in a kind of equilibrium. There's collisions, there's radiation. Given enough time, it'll form into a state where there's no longer any change with time in this level. It's equal to 0. And that gets us. This is where I'm going to mess it up badly. Yes, correct. So we have a formula that tells us how many levels in the upper and lower state. If we know the collisional constant, that's a quantum mechanical parameter we have to look up. The Einstein A coefficient, which is a quantum mechanical parameter, although we can, if we know the transition moment, we know we can calculate that from the transition moment. And the density of hydrogen. And so there's a definition of one particular density. If NH2 equals A over Q, then this is so if you have a density which happens to be A over Q exactly, then you end up with an equal number of particles. So that's kind of a special level called the critical density. And if you look at some of these numbers, for carbon monoxide, the Einstein A coefficient is 7 times 10 to the minus 8. What that means is if you have an excited carbon monoxide, there's a probability of 7 times 10 to the minus 8 that in 1 second it'll fall down. Meaning it'll take 1 divided by 7 times 10 to the minus 8 seconds for it to happen. So the lifetime of CO J equals 1 to 0. So if you have a CO level in the J equals 1 level, falls down, irradiates, that's about equal to 1 over 10 to the 8 seconds. So that one takes a long time. On the other hand, if you consider the collisional rate, this is how easily the hydrogen will push it back up a level. That's 5 times 10 to the minus 11. It's even lower probability. Meaning that if we put these numbers in here, the critical density critical density is 5 times 10 to the minus 11 divided by 5 times 10, 7 times 10 to the minus 8. No, sorry, 7 times 10 to the minus 8. The radiative, the Einstein A coefficient for carbon monoxide, divided by 5 times 10 to the minus 11, that's 10 to the 4. So if you have 10,000 particles in a cubic centimeter, then you're at this critical density where you have the same number of carbon monoxides in 2 levels. That's the idea. Okay, so we've talked about the case where there's collisions and radiation, these kind of competing effects. Radiation goes down, collisions pushes it up. And if you talk about the case where you have this room with so many collisions that you definitely have an equilibrium between the velocity energy of the particles in the room and the rotational energy of the particles in the room. The reverse case is if you have such low densities, there's never a collision. So now you have the rotational energy of the particles in the room and no collisions. Turns out that in the universe, that's not the only way for a particle to be excited, collisions. Also, you have the cosmic microwave background. And so this maybe is related to the heat death of the universe, I guess, in that this spectrum shows the intensity of radiation left over from the Big Bang, curve like this, which might possibly look like a familiar curve to you. The formula for this, I think I've written down somewhere still, is, yes, the cosmic microwave background radiation is a black body radiation field, just like a star, in fact. And so, yep. So the intensity of radiation, so that means, in this case, I'm going to say photons per centimeter squared per second per hertz. No, let's make it meter squared even, per second. This is the number, per hertz. This is the number of photons that will strike your face in 1 second, basically, which is not a lot from the cosmic microwave background. Okay, which is another pretty awful formula. What we have here is, this is not a V, this is a nu. I guess you've probably come across this in your academic lifestyle. A V looks like that, and a nu looks like that, unless you're using Microsoft Word, in which case a V looks like that, and a nu looks like that. So Microsoft Word. Times New Roman do not get that one right. So this is a nu, and nu in this case is the frequency. So that's the energy of a photon is equal to h nu, Planck's constant times its frequency. So at a particular frequency, in this graph, in this case we have frequency. The units are wave numbers, but it's a frequency graph, believe me that. And then you have some numbers in the front, and you have an important thing here, including an exponential. And if we take the assumption that nu is reasonably large, and we ignore the constants, we have some number, called some constant. And if nu is quite large, we can ignore this minus 1. So h nu, that's the energy of the photon. So in this case, we have energy over a temperature. This is exactly the same. It's not the same formula exactly, but it's the same, very nearly the same formula as the Boltzmann distributions and the Maxwell-Boltzmann distribution for particles in a box. And that's because we're once again dealing with the same idea of many particles which are all statistically independent and interact in an undefined way, produce the same shape. And that's actually what this graph is showing. And the important case in this case is that this peak This is where the cosmic microwave radiation is strongest, occurs at about 6 wave numbers. Yep, the graph. So, and so if we go back to this line here, this shows an astronomical observation, the first molecule identified in space, not the first one detected. That was the diffuse interstellar bands. And there were 2 lines here. This is a stellar absorption line shining through an interstellar cloud. And on the way to the cloud, there's some other absorption lines up here. And these 2 are both due to the CN molecule. So the CN molecule, CN and N, and it's asymmetric, so it has a dipole moment. We know it has rotational transition moment, not 0. And it has a rotational constant describing the separation of its levels. 1.9 wave numbers. This is the energy unit we use in spectroscopy. You'll get used to that later. Okay. And so the peak of this radiation field is at 6 wave numbers. So the transitions of CN, this, J equals 1, J equals 2. The first possible transition is from the J equals 0 to J equals 1 level. And if we know the rotational constant, then we can say, and you have it written on your piece of paper, that has an energy, that transition, of 3.8 wave numbers. This one, J equals 2 to J equals 1, has an energy of 11.4 wave numbers. So the photons that you need for these 2 transitions, one is just left of the center, one is just to the right of the center. In fact, the one on the just to the left is a little bit closer to the peak. So that transition is more likely to happen if you have the cosmic microwave background radiation providing the photons you need. And the final thing I want to note was this transition has a name. It's called R0. This transition has a name called R1, and that was on an extra slide I put in the last time. It's not actually that important. The point is the 0 means the transition begins, the lowest side is J equals 0. The 1 means the lower level is J equals 1. The R means that the photons are going, well, the upper level is 1 higher, actually. That's the effect. And so these 2 transitions, the R0 line, if you can see it, is a little bit stronger than the R1 line, meaning that this transition is more likely to be excited by the cosmic microwave background than this one. And that's because that line is a little bit closer to the peak than the line on the other side. So what that means is that this observation, 1941, I don't know, who knows their Big Bang theory? When did they discover the cosmic microwave background? Yeah, I'm looking at you. Or anyone, for that matter. When did Hubble identify, when was the cosmic microwave background identified by observing the radiation? I mean, I realized Jansky was the first detector that might detect it, but who actually? Okay. Okay, anyway, the point is that by looking at these 2 molecules and that microwave background, you can actually determine cosmic microwave background temperature just from that spectrum, from that chemical spectrum. And that was my point. Yeah. And so in this case, what we have is we have the energy of the radiation from the cosmic microwave background producing a level population here because of whether or not these transitions are at the peak of the energy distribution. So the temperature of this radiation field, 2.7 Kelvin, that's what, 60? The 60s. Right, okay, right. So this is 1941. So people measured the CN lines. They said there must be a radiation field affecting the CN rotational levels of about 3 Kelvin. That was and by that point they didn't know that this was left over from the Big Bang. This is a pre-detection without realizing it. Okay, so anyway, so this radiation has a temperature of 2.7 Kelvin. That could go in the formula for the black body radiation formula. And then the excitation levels of the CN molecule will match this temperature of the radiation as long as there's no collisions. So if the density is really low, there's no H2 collisions to affect the rotational level distribution, the excitation temperature will equal the radiation temperature. If there's very many collisions, then the excitation temperature will equal the kinetic temperature. If you have some collisions in between, you have to worry about both of these things. And that's why we want to know the critical density. If you know that if your density of your hydrogen is about the critical density, you can't ignore radiation and you can't ignore collisions. They're both important. Yeah. Okay? So what if they're both important? How do you calculate your level populations? And if you remember, when you're solving a spectroscopic problem, you want to know the energy levels of your molecule. Then you want to know the populations of each energy level, and only then can you calculate what the spectrum should look like. So we need to know that. We'll stop in 9 minutes, if you like, for a break. Okay, so here's another differential equation. Here's another two-level system. This time we've got photo emission. This is the Einstein A coefficient controlling that. So we have some levels in the upper state, 2. And this is how much 2 is changing, the rate of change per second, due to things like photons being emitted. And it's minus A into A, because that's because the photon is decreasing in population. We have hydrogen atoms creating collisions and increasing rotation. That's NH2, N1. If you're going to have a collision, we need to have a population in the lower state. That density is here. The number of hydrogen atoms, the density of hydrogen atoms, and the quantum mechanical parameter Q. That's that arrow. Then we add a third arrow because collisions can also have the opposite effect. You can have two molecules collide, and then they rotate slower at the end. So there's actually 2 paths to consider here. So there's another negative sign due to that effect. There's 3 ways to change the populations. Eventually, though, if you put in some energy, put in some particles, they'll eventually reach an equilibrium, meaning this level won't be changing at all. The number of particles in the box that have energy level N2. Set that formula to 0 and rearrange it, which I'll leave you to do. Then you can end up with an equilibrium solution where you have a ratio of upper level particles and lower level particles. Meaning if you have total number of density of particles in your box, usually per cubic centimeter, if that was 10 to the 5, then we want to know how many levels, that's right. And some of those levels are in the J equals 1 state. Or N1 state. And some of those levels are in 2 state. Add them all up, eventually you're going to have the total number of particles in the box. So the total number of particles is included, and then the ratio of these 2 levels can be calculated based on the critical density and the Einstein A coefficient and the collisional parameters. That's what this formula is giving us. There's one problem, however, which is that the Q factor I showed you before, that was telling you what is the quantum mechanical rate at which a collision with an H2 molecule will push a particle upwards. Now we want to know the rate for collisions pushing particles upwards and downwards. And it turns out those 2 rates, this is the particle going up from 1 to 2, 1 to 2, 2 to 1, 2 to 1. And there's an equilibrium between those 2 rates depending on the kinetic temperature, the energy of the 2 levels, and the degeneracies. That was the number of ways you can have a rotational level over the same energy. Okay, so that was that idea. So if we know the 2 parameters Q and A and the hydrogen density, we can work out in the 2-level approximation the ratio of particles in these 2 levels. Okay. And I won't go into this in too much detail because, of course, we saw there's a whole stack of rotational levels, not just 2. In fact, there's 4, but there may be many more than 4 may be important. And there's photons being emitted all the time. Photons can decrease rotational level one unit at a time. We can have collisions going up and down between the first 2 levels, like before, or between the next 2 levels, or between transitions which are between rotational levels which change J by a factor by 2, or even 3. All possibilities are on the table. That's why this is kind of a a field where you don't want to get, maybe you don't want to get into the business of calculating the collisional coefficients because you're going to be there for the rest of your life. So the differential equation I showed previously showing the 3 terms up, down, and down with photons really needs to have all these terms. It's a much larger problem. And each of these collisions has a different Q coefficient. And this is a graph of Q coefficients. This is, if you had carbon monoxide in a box, this graph, by the way, is different from the one in your notes because I fixed an error. It started in 1 in your notes. And of course, the lowest rotational level of carbon monoxide is J equals 0, not J equals 1, so I'd put those in the wrong scale somehow. Anyway, so there's 3 curves here. This red one shows the coefficients that move between adjacent J levels. The first number is from J equals 0 to 1, and then it increases. The J equals 2 levels is they go between levels that differ in rotational levels by J equals 2. And in some case, that can be more likely to happen than even the J equals 1 transition, delta J equals 1 transition. And the delta J equals 3 transitions are somewhat less likely to happen. And so there's actually an entire differential equation, which I won't write up, but so that the population of each level has its own differential equation in terms of the rate of change, and it has not just 2 parameters, but we need a term for every single arrow connecting that level to some other level. So this is known as the non-LTE approximation, an LTE. Local thermodynamic equilibrium. And so if you have local thermodynamic equilibrium, meaning where you are in your box, the particles are colliding so fast that you're always going to have collisions converting kinetic energy to rotational energy, and you'll have the same temperature of the rotational excitation and the kinetic excitation. If that's not the case, then you have an effect which is non-local, meaning that photons are appearing. You have the effect that it's no longer equilibrium, so that you have either the case where you have such a low density that collisions are not frequent enough. Collisions are not frequent enough to re-pump the particles into their high levels once they radiate away energy spontaneously. Or alternatively, you have so much radiation, for example, the cosmic microwave background radiation field, that you need to include other effects, which I haven't discussed here, even, which is another kind of effect where you now have a photo transition that goes upwards. So this is photo emission, the Einstein A coefficient. This is the photo absorption, the Einstein B coefficient. And we won't worry about that too much in the future, but this is even more terms added to your differential equation. So actually, this problem is even larger. Okay, and so that's all the microphysics. The question is now, how does this apply in astrophysics? So I've drawn a cartoon diagram of an interstellar cloud. And the idea is that the observer is looking at a cloud, and because we're talking only here about rotational spectroscopy, we're probably observing the cloud with ALMA or another millimeter or submillimeter telescope. And we're seeing several things. We're seeing, first of all, possibly there's a star behind the cloud. This is like the Rho Ophiuchus situation. We have some radiation passing through the cloud and being absorbed, and so you can see the absorption lines in the stellar radiation. This is not the case we actually find if we're looking at rotational spectroscopy, because the star doesn't produce a lot of millimeter radiation. It doesn't act as a good background radiation source for that. In this cloud, we have a certain density, which we'll assume to be the same everywhere. That's of course, if this is complete vacuum, density of n equals 1 particle per cubic centimeter, and this is 1,000 particles per cubic centimeter, in reality there's going to be some kind of gradient near the edge, but that's generally neglected. There's some kind of kinetic temperature in the cloud, meaning the Boltzmann distribution of Maxwell-Boltzmann distribution of velocities. There's some kind of excitation temperature, meaning all the particles are rotating at some speed or another, and that distribution is the Boltzmann distribution, rotational levels. And so that interaction of whether these two temperatures are the same or not is going to depend on the density. If it's a high density, they will be. If it's not, they won't. Alternatively, this has been irradiated by the cosmic microwave background. So there's a third temperature, the radiation temperature of the black-body radiation coming into the cloud. If it's very low density, this excitation temperature of the rotating molecules will match this temperature. If it's intermediate density, it'll be somewhere between these two temperatures. We shouldn't forget the fact that this cloud is not just rotating molecules, it's also dust. In fact, it's the dust that you see mostly if you look at a cloud in the visible. It'll become opaque because the dust is absorbing all the starlight. But even in the submillimeter, there can be some dust emission if it's a cold black body dust emission. So there's some radiation which you can potentially observed from the cloud due to the dust. And finally, there's radiation due to the fact that the molecules are emitting photons. They spontaneously emit and decrease their excitation temperature, producing radiation that you observe. And that's exactly what Elm was observing. So this is actually, I think, pretty much a complete picture of all the excitation temperatures and photon emission absorptions going on inside the cloud. That's the complete picture. And
when you get a spectrum of a given source, how are you sure you are not your spectrum is not contaminated with another source? For example, you look at this, you have a source, and then between the observer and your source, there are another molecular emission. So how
Yep.
are you sure?
Yep. Okay. So in this case, you're saying, does this red arrow get confused with this green arrow in this particular diagram?
Yeah.
I guess. Well, so
So you're sure your spectrum, the lines are the lines in the
exactly.
source?
Yeah. Yep. So the source I kind of was trying to draw was a star. So in that case, if we so if it really is a star, the big red star there, so that's frequency. Now we'll stick with wavelength. Wavelength. And this is the spectrum that the telescope's observing. So the star has a black body spectrum going down. Of course, we also saw the star has stellar absorption lines within its own spectrum. So that kind of shows up as well, and down here. And then the emission from the molecules, that's only occurring at the resonant frequencies of the rotational transition. So there's small lines appearing here due to the molecules. That's basically the idea. The bigger problem is if you have an interstellar cloud like this, and another interstellar cloud. So this one is radiating molecular emission, which then gets passed through there, adds its own radiation along the path of the way. Yeah. Or, like I said before, these interstellar clouds have a gradient within them. Perhaps the temperature is cold in the middle and hot on the outside, and the temperature is going to affect the collisions between molecules. So then you have emission coming from different layers within the same cloud, which is not really the same emission in terms of the populations of the levels. Yeah. Okay. And maybe we'll. Maybe that's actually a good place to have a break. That's right. The time now is 3:34. We could begin at 4 o'clock. That would be a round number to easily remember. It'll give me time to finally remember to look at my talk slower sign, which I didn't do, I know. No one told me to do it. That's part of the problem. 4 o'clock, and then we'll keep going.